Hi guys, in today's video we are going to do some examples of equilibrium of a rigid body in the case of a 3D system. Empat babe. Okay, if you look at this example, you are given a case of a homogeneous plate which have a mass of 100 kilogram, and the plate is subjected to a downward force of 300 Newton, and it have a couple moment at the end of the edge over there with a magnitude of 200 Newton meter. So if you notice, this plate is supported at point A with a roller joint, and then there's a ball and socket joint at point B, and there's a cord at point C. So you are required to calculate the components of the reaction forces at these three supports, which is at point A, point B, and also point C. Since they did not show you the X, Y, and Z axis, so you have to illustrate the X, Y, Z axis on your own. So quite easily, since this is a rectangular plate, we are going to take the X axis over here, Y axis over here, and Z axis over here. And now you have to draw the loads which is subjected to the body. So given the mass of the plate is 100 kilograms, so we know that the weight of the plate is equivalent to mass multiplied with gravitational acceleration, mg. 100 times with 9.81 will get a value of 981 Newton, which is acting exactly in the middle of the plate. Okay, the next thing you need to do is you need to draw all the reaction forces at the supports and joints. Okay, so looking at point A, you have a roller kind of joint. So this roller is only constrained in the direction of z-axis. So therefore, there is a reaction force in the z direction. We are going to call it AZ. Next, moving on to the next joint, joint B is a ball and socket joint. Because of the design of the socket, it kind of constrains the movement of point B in all X, Y, and Z direction. So therefore, there is a reaction force in X direction, by which we are going to call it Bx, and then there's another reaction force in Y direction, we are going to call it By, and the movement is constrained in the Z direction, so therefore there is a reaction force in the Z direction, we are going to call it Bz. Okay, last but not least, at point C, there's a tension cord over there. Quite easily, you can just draw the direction of the tension cord following the lines of the tension cord lah. So we are going to call this CZ because it is acting purely in the Z direction. Okay, bila free body diagram kita dah complete, then only we can apply the equilibrium of forces for us to do the calculation. Okay, so let's start with summing up all the forces in X to be 0. So there's only one component in X, which is Bx, so Bx is equivalent to 0. Okay, move on to the next equilibrium condition, summing up all the forces in Y to be equivalent to 0. Again, there's only one component in By, which is over here, and it is 0 Newton. Okay, last but not least, we can sum up all the forces in the Z direction to be 0. So let's see what's there in Z direction. There's one AZ pointing upward, so it's positive AZ, and then your BZ is pointing upward, that's plus BZ, and CZ is pointing upward, so plus CZ, and then there's 300 Newton pointing downward. Okay, so it's become negative 300, and your negative 981 Newton, the weight of the plate is pointing downward, so it's negative 981. All that sums up to 0. Okay, it's a good practice. All the unknowns, you put it at one side of the equation. So AZ, BZ, and CZ, put it on the left side of the equation, and the known value you transfer it to the other side of the equation. Okay, since we cannot solve this particular equation, you move on. Okay, so let's just name this equation to be equation number 1. Now let us move on to the next strategy. Since we cannot solve it based on the equilibrium of forces, then we have to apply the equilibrium of moment for us to generate more equations basically. Okay, so in the case of a 3D system, you can quite easily apply a moment about an axis. Okay, so in this case, let us take axis BC as our reference rotation axis. The reason is because we want to cancel out the moment produced by any loads happening at point B and point C. Okay, so quickly recall, moment is equivalent to F equivalent to D. Okay, so summing up all the moment of force along BC axis to be equivalent to 0. So there's no moment produced by any loads subjected to point B and point C because the loads passes through the rotation axis. So therefore, there's no moment produced. Okay, so looking at AZ, it is acting at a distance of 2 meters meter from the rotation axis. And using your right hand rule, okay, using your right hand rule, you can see your thumbs is actually pointed to the negative BC axis. So therefore, in our equation, it becomes negative. Okay, so accordingly, 981 is pointing downward. It is acting at a distance of 1 meter from the rotation axis of reference. And using your right hand rule, your thumb is pointing to the positive BC axis. So therefore, in your equation, it will become positive 981 multiplied with 1. And similarly, 300 Newton is in the positive direction, positive moment direction, using your right hand rule, and it is acting at a distance of 2 meter from the rotation axis BC. Okay, that's about it. So all that sums up to 0. There's only one unknown in your equation, AZ. So quite easily you can solve for AZ to be 790.5 Newton. Okay, moving on, let us look at what other axes that we can play around with. So looking at axis AB, I can see there are multiple loads acting at point A and point B. So we are going to apply moment about axis AB so that we can cancel out the load subjected at point A and also at point B. So therefore, summing up moment about about axis AB sums up to 0. So let's see, there's CZ over here, and it is acting at a distance of 3 meter from axis AB. Okay, and using your right hand rule, you can see your thumb is actually pointing to the positive AB axis. So in your equation, it becomes positive CZ. Okay, so next, 981 is acting at a distance of 1.5 meter from your AB axis, and using your right hand rule, it is pointing to the negative AB axis. So therefore, in your equation, it becomes negative. Alright, and accordingly, your 300 Newton is acting downward. Using your right hand rule, your thumb is actually pointing to the negative AB axis. So multiply with the perpendicular distance of 1.5 meter. Okay, and don't forget there is a couple moment at the end of the edge over here which is acting in the same direction of the AB axis. So you have to include that in your equation. So that 200 Newton meter is actually your moment. So you don't have to multiply it with any distance. And the direction, okay, looking at the direction of the moment, the axis is pointing to the negative AB axis. So therefore your equation becomes negative 200 Newton. And that's about it. So all of that component sums up to 0. So quite easily there's only one unknown over here, by which your CZ can be easily calculated as 707.17 Newton. Okay, so now since you have the magnitudes of AZ, you have the magnitudes of CZ, you can just substitute these two values into equation number 1. And you can calculate the BZ to be negative 16.67 Newton. So negative is an indicator that the actual direction is opposite to your initial assumption. So if you look at the figure, initially you assume your BZ to be pointing upward to the positive Z direction. But since your calculation is in a negative magnitude, so it means the actual direction of BZ is actually pointing downward to the negative Z axis. Okay, so that's about it. This is how you solve the problem of equilibrium of a rigid body in the case of 3D system. Okay, till then, see you later, alligator.